hobby to look into IPv6 for, I don't know, like 10 years or something now. And since we do managed services, we can pretty much just determine what goes on inside of our data center. So we have some flexibility in deciding how we deliver the services, and that means we can do v6 if we want to, because the customers, they don't really care as long as the website works. That's kind of what we actually are delivering in the end. So when I started looking at it, I'm looking at how do we go about delivering v6? How do we get to a point in time where we just do v6? Because after all, that is the end goal, to have a v6 only world. And I missed Geoff's presentations earlier this morning, but I heard that actually he talked about some of this stuff already. And if you start out with v4 only, which pretty much all of us, I guess, have some experience with, the next logical step, if you do a data center service, is to do some sort of translation in front. So you leave the bulk of your data center v4 only, and you do some sort of translation or proxying, something like that, all the way in the front end where your clients come in, or in front of that actually, so that you can present a v6 personality to the world. The next step would be to actually identify those servers or applications inside of your data center which speaks directly to your internet clients, like the web servers, like the mail servers, and so on. You put v6 on those in addition to the v4, so you dual stack them, but you leave everything behind, like the database server, the file server, etc., v4 only. And if you move along the spectrum to the middle, it will be to actually do v6 in parallel with v4 everywhere. And that's dual stack. That's the recommended way to do it, or has been for quite some time. But if you imagine you go further, well, then you start turning off v4 in the back end, but you leave the v6 on, v4 on the web server, on the mail server, etc., etc. And going further towards v6 only, you might turn off v4 on the public servers as well, and deploy some sort of translation layer in front. And eventually, when you don't need that, you can turn it off, and you're v6 only. So when I try to look at what benefits and disadvantages these things, or these various stages have, I noted that, well, v4 kind of sucks. And that is for multiple reasons. We don't have enough addresses to kind of deliver our services using v4 addresses for eternity. It doesn't work. So you can do NAT. If you do NAT, that has the disadvantage of you actually have to route you have to put a default route in your network that points to the stateful NAT device, because otherwise it won't work. And you need to actually make sure that the traffic goes across that same NAT device in both directions. And when you use private addresses, which we do because we don't have enough public addresses, well, we constantly run into problems with customers wanting to deploy some sort of VPN into their infrastructure in our data centers, and it's collisions and it's renumbering. And if they are actually growing faster than we have set aside space for on their server lands, well, then we need to actually expand those lands, but we can't because the next subnet is taken. So then they need to renumber as well, and this is a pain in the ass. And, which is interesting for me, over in Norway, we have this public sector thing that decides what the government needs to require when they actually go out and buy stuff from the private sector. And in the latest draft of this catalog of requirements, they are requiring IPv6. And as I think many of you know, the Norwegian public sector is filthy rich, and as a private enterprise, we want part of that money. And that means very soon that we actually have to deliver IPv6 or we're disqualified immediately. So the next step is this dual stack thing. The dual stack means IPv4 everywhere, I just told you many reasons why dual stack sucks. Well, IPv4 sucks, and dual stack sucks for all of those reasons as well, because it requires v4 everywhere. And in addition, it brings up the complexity in the infrastructure by a very large amount, because you actually need to configure all your applications to listen on both v4 and v6. You have to set up firewall rules for v4, v6. You can thumb type something on v4 and v6 in both those protocols, and if something stops working, you actually need to debug all the various stages in your application on both protocols. And it might be across, so you can have a web server that speaks to the file server over v6, but the file server speaks to its iSCSI backend over v4 again, and you have all these different permutations, and the complexity of it all becomes very, very large. And of course, you hire people, they need to actually know both of these protocols. So it becomes very complex. So we don't like the idea of dual stack either, plus, as I said, it doesn't help us with our problem of running out of v4 addresses. So if I started looking at what actually can we do today, well, actually all of them would work for us, because our products are typically a website that needs to be online and available from the internet. So like I said, it doesn't matter what we do inside, as long as the front end has availability from the entire internet, whatever that means. But it does mean IPv4, because around 4 in 5 people have only v4 internet connectivity. But if I look at how to go through this constant, let's call it renewal process, to move further and further along to the end goal of v6 only over time, over many, many years, it makes a lot of sense to just skip all the intermediate steps and just go as far towards the goal as you can, stop there, and then wait until you can actually go all the way, because that depends on external factors which I can't control, as in all of you guys and all of the other internet providers everywhere on the planet. So I decided on what's best for us is to try to work towards a solution where we have IPv6 only in our data center. Oops, that slide was not supposed to look like this. Anyway, the idea is to have the data center IPv6 only. All of the stuff inside of the data center, which should have been on that slide, like your file servers, your web servers, your load balancers, your firewalls, your switchers, your routers, your everything, just v6 only. And then, between the IPv6 only data center and the IPv4 internet, you put a translation layer, which just does that. Translates from the v4 into v6, and once it passes that translation layer, it's v6. And you only need to care about v6 inside the data center. And fortunately, there is a technology for this already. Basically, the idea is that you take a /96 prefix. And it's /96 because 96 plus 32, which is the IPv4 address space, equals 128. And then you can take any v4 address that exists, and you can put it after that 96-bit prefix, and you have constructed yourself a v6 address. So if you have this v4 address 2030 blah blah blah, and you put that next to this prefix, well, then you have a v6 address. And you can actually write it like that, and it ping or whatever software you're using will recognize that as a v6 address. And then that's how you basically represent the entire IPv4 internet as part of IPv6. So the next challenge then is how to make those v6 only web servers or load balancers or whatever it is inside of your data center that do not follow this address, this magic address format, to make those available. And the idea that I came up with was to basically make a static mapping table. So that if you have a /24 or /22 of public v4 addresses, you can make a one-to-one mapping between a v4 address and a v6 address, presumably inside of your data center. And then you have everything that you need to translate between v4 and v6. So this is how it works. I called this SIIT-DC. SIIT was a pre-existing standard. That's the mapping v4 into v6 part. And DC is the addition of this static mapping table for data center usage. So it means static IP ICMP translation for data center environments. That's a mouthful. So this is how it works. Imagine you have this v4 internet on the left. You have a v6 data center on the right, and you have one client on the internet needs to speak to this v6 only server. And you have these boxes in between that are supposed to do translation. And those are called border relays because they sit at the border between those two, v4 domain and the v6 domain. So the client would typically just look up in DNS what is the host IP address, IPv4 address of the website or whatever I'm visiting today. And he will get back a public v4 address. That public v4 address gets routed to one of these border relays. And that's standard routing. It's BGP or OSPF or static routing, whatever you prefer. So what happens when this relay receives this IPv4 packet is the following. First, it takes this predefined /96 prefix, which has been set aside for this purpose, and prepends it to the source address. So you can see the client's original source address became this IPv6 address. The destination address gets swapped in accordance with the static mapping. So there's a one-to-one mapping between this IPv4 address and this IPv6 address, which happens to be the IPv6 address of the server. So it make a table lookup, swap, done. Everything else in the packet that matters, like the TCP headers, the port numbers, the HTTP payload, everything else, it's just a copy. You don't change it, you just copy it verbatim. And now you have an ordinary v6 packet, which the border relay just drops into the v6 network. And the v6 network will figure out how to actually take that packet to the web server, which is, again, same way if it's BGP, static routing, OSPF, ISIs, whatever you prefer, because it's just an IPv6 packet. The server, when it receives this packet, again, it's just an IPv6 packet, so it will just respond to it by giving a HTTP response or something like that, or a SYNAC or something. Of course, then with the source and destination addresses swapped, which is common, how it's done, and it gets dropped back into the IPv6 network. And now there's the trick, which is that this /96 prefix, 2001 DB8 in this case, is also routed to these border relays. And it doesn't have to be the same border relay. It can be any other border relay because there's no state kept. It's just a packet-by-packet stateless operation. And I'm guessing that most of you can already predict the next slide, because it is that simple, which is basically that this source address, again, it's a one-to-one exchange, a swap, according to that mapping table, whereas the prefix of the destination address gets cut off. And now you have it. The loop is complete. Of course, the layer 4 payload, like the TCP, contents, ports, whatever, again, a verbatim copy. So this response packet here, it looks exactly what the client expected to receive as a result of sending this packet. And the same with this response packet here is what any IPv6 server would expect to send as a result of this original request packet. So from the client's point of view, it's speaking to an IPv4 server, normal IPv4 server. From the server's point of view, it's speaking to a v6 client. They don't really have to know that this translation is going on. So that's the gist of it. It's really that simple. And it allows us to run v6 only in the data center, because we can put these border relays out on the edge of our data center and have all the v4 stuff stop there. But a nice feature of this, which you don't necessarily get with regular stateful v4 NAT, is the fact that the original source address of the client is actually maintained. That information is not lost. It gets carried into the server. And that means that the server can do, say, geolocation. If it needs to be taught how to strip that prefix, but it can recognize it and then say, okay, this is a v4 client, so I'm just going to look up in a v4 geolocation database, or I'm going to look up the abuse address for this v4 address, etc., etc., to actually not completely lose the knowledge that this is a v4 client and what was his original address. And like I said, it's stateless, so it was very intentional that I put 2 of these boxes up on the slide. It's because it doesn't matter if it travels, if the SYN travels via one box, the SYN ACK comes back via another one, and the final ACK comes back via a third one. It doesn't matter because there is no state being kept. And that is a very big advantage compared to v4 NAT, in my opinion, because the session tables and the connections per second numbers are usually what kind of limits a NAT box from performing at a line rate. So that was it. And of course, since everything inside the data center is v6 only, now my developers, they only need to know about v6 or care about v6 really. They don't really have to write dual stack software anymore. They can write single stack software. They can test a single stack. They can monitor, the server admins can monitor a single stack, and if something goes down, they only troubleshoot a single stack, because it's either v6 works, and if v6 works, then v4 works as well, at least for their point of view, no train of thought there. Anyway, yeah, it's v6 only thing to worry about inside of the data center. So it's only me and a few colleagues that actually operate the translation system that actually need to worry about v4. And of course, when we actually get to that point in the future where we don't need v4 anymore, if that is 10 years, 20 years, 50 years from now, it's easy to decommission because we can just turn it off, and we have no dependency on v4 inside of the infrastructure, inside of the application delivery stacks. But even though we do manage services and we can, to a large extent, decide what kind of applications we are running to provide our services, sometimes a customer comes dragging along with some sort of service or application that they bought from some ISV and they want to run that, and maybe that doesn't support IPv6 well enough. Fortunately, there is a way to solve that as well. And it also is based on the fact that this solution is stateless. And you basically take the translated packet that comes into the server and you translate it again back to v6. So it comes in from the internet as v4, passes the border relays at v6, and then comes to the server where you translate it back to v4 and passes it to the application on some sort of virtual internal-only interface. And then the application can just see, okay, this is a v4 packet and a v4 client, and I can deal with that as v4. And it doesn't even have to support IPv6 at all. It cannot bind only to that v4 virtual interface if it so chooses. And if any of you are familiar with 464xlat, which is a technology that allows mobile operators to do v6 only. I know of at least one Swedish mobile operator that's planning on deploying that soon. It's pretty much the same thing, except for the fact that it's end-to-end transparency of IPv4 addresses. So that virtual interface on the server will have the public IPv4 address assigned to it. So there's no NAT of v4 addresses. So you can run encrypted FTP across this if you want, and it will work. Try that with a NAT, a v4 NAT. So yeah, like I said, really, really simple. I like simple stuff. I don't like complex stuff because complex stuff are very difficult to debug when they go down and when they stop working. So what you see on the right there, that's all you need to do to deploy what I put in this presentation today on a Cisco ASR box. Because I put in this support when I asked them to. I thought it was a good idea. And that is, I don't know, 4 or 5 lines of code plus 1 line per entry in that static table. And all of these, the non-bold text is just standard routing, which is not directly related to this SIIT stuff. So really, I mean, I think you can get away with 4 or 5 or 6 lines to do a border relay with only 1 mapping. But there's also open source implementations, both user space and kernel space. We are using the one that's called Joule. We're very happy with that one. And for those virtual interfaces, we're using SIIT-DC, which is basically just a Perl script I wrote that sets up this stuff in the Linux kernel. But there are other implementations as well. So the final thing I just want to mention is that this does not require you to run v6 only in your data center. It facilitates v6 only in the data center, but it doesn't require it. So if you have dual stack in your data center, then that's fine. You can run SIIT-DC on top of the v6 connectivity in your dual stack data center if you want to just play with it and test it. You don't have to commit to turning off v4 or native v4 or native dual stack or whatever you have already. But you need v6 because essentially what this does is to make v4 a service, an application that gets delivered through the v6 network. So that's basically it. And I hope you understood it because if there was one thing I hate is that when I come to these kind of conferences and then somebody is presenting a super cool solution which is so complex that I have no idea what I actually just saw in this half hour. But I hope that at least some of you actually, I can understand how this works because then I actually achieved what I came here to do. So that was my presentation. If there are any questions, I'll be happy to take them. If there is time, I think so.
So we have a few minutes for questions for Tore, if anyone has any. Think they want clarified? No, then I guess it's... Oh, yes, microphone at the back, please.
Okay, I'll try to do it in English. Michael Lundblad is my name, and I work as a consultant. And I'm kind of confused in this scenario here. How do we handle protocol with embedded IPv4 addressing information like FTP?
Then you would need this double translation system.
Okay.
Yeah. So basically, if you do the double translation, you can look at it as a v4 tunnel. Even though it's not a tunnel, it's a header swap and then reswap, and it becomes end-to-end transparent, which is why encrypted FTP, which does pass v4 addresses inside of payload in an encrypted way, so NAT can't actually rewrite them even if it wanted to, it will work. But you want, with a single translation mode, it doesn't work with those protocols, so that is correct. So
Okay,
that's why they have the double translation system.
Any more brief questions for Tore? No? Well, then join me please in thanking him for a very clear presentation.
Yeah, thank you.